A vase sitting on a table exemplifies another important force that we need to consider when solving problems with Newton's laws. That vase manages to sit there at rest without falling. On the other hand, if we simply hold a vase out in midair and let go, we know that it would accelerate downward due to the force of gravity. The question is, why doesn't the vase sitting on the table fall? Since it's not moving, it needs to have an acceleration, which is 0. And we know by Newton's second law that the net force divided by the mass of the vase has to equal 0. Net force means the sum of all forces acting on the vase. Remember that the force and the net force are vectors, and we need to take the vector sum of all the individual forces from any source acting on the vase and add them together as vectors to make the net force. In any kind of problem like this, it's best to have a coordinate system, and we'll set up something where the horizontal direction over this way will be the x direction, and the y direction will be the vertical up and down away from the floor. Well, there is no force in the x direction in this case, so we'll only worry about y. In the y direction, we have the force of gravity pointing straight down, and as we said before, the gravitational force acting on an object near the surface of the Earth is equal to the mass of the object times little g, where g is this constant 9.8 meters per second squared. That's not the only force out there acting on this vase, or at least it can't be, or else I can't get the net force to equal 0. There absolutely must be something pointing up. We're going to call that force that's pointing up the normal force, the thing that's created by the table, the lift that the table provides to help the vase not fall. And looking at this vector equation here, we know that this net force has to equal 0. So when we create an expression that says net force is 0 in the y direction, it's going to look something like this. This is, on the left-hand side, the sum of all the forces in the y direction. This force, which we're calling the normal force, points in the positive y direction, so I'm writing a positive number right here. This force, the gravitational force, points down against the y direction, so we're giving it a negative sign right here, because it's pointing in the minus y direction. So the expression, the net force, total force on the left-hand side is n minus mg. This has to equal 0. And why is that? Because the acceleration equals 0. Solving, we have an expression then that allows us to calculate what the normal force must be in order for this vase to stay at rest. We've derived that the normal force equals mg, at least in this particular case. Now I will emphasize that this is not a general formula for the normal force, but one that works for this particular case of a horizontal tabletop. The things that are generalizable is that this thing called the normal force is always pointing away from the surface, the hard surface that's holding something up. So the word normal in mathematics is another way of saying perpendicular. So it might have been nice if physicists had called this thing the perpendicular force, but we don't call it that. We call it the normal force. And the normal force is always pointing perpendicular to the hard surface that's lifting something. It's always that way. So whenever we want to draw a normal force, always draw it perpendicular to the surface, wherever the surface is pointing in that direction, in that particular instance. The other thing that's often the case that we can do with these problems involving the normal force is that we can calculate what its value is by simply saying that the object is not flying off the table or the object is not lifting off of a particular surface. Because in this case, the y direction, if we choose it carefully, points away from the surface, and if the object is remaining on the surface, then the acceleration has to equal 0 in the y direction. So if we can choose y to be perpendicular to a surface, that will help us, because then we can calculate what n will be by setting, as a general technique, y equal to 0. Here's a practice question. Consider a cart rolling down a roller coaster as shown in this particular figure, and we can imagine that its speed will change as it rolls on down the roller coaster. Of the 5 choices shown, which is the best answer that would be true about the cart's speed and the acceleration, or at least the component of acceleration in the direction of its motion? Is it the case that both decrease, both the speed and the acceleration in the direction of motion decrease? That speed decreases but acceleration increases? That speed increases but acceleration decreases? That both increase? Or that speed increases and acceleration is constant? Well, the correct answer is that the speed is increasing, but the acceleration decreases. How do we analyze this problem? Well, first, we will note that the acceleration is always in the same direction as the motion of the object. So if the velocity vector is pointing down, the acceleration is pointing down. So v, the velocity, has to be increasing. So we're looking for an answer like C or B or E, where velocity is increasing. And that's because acceleration is in the direction of motion. Now, what's the trend for acceleration? Well, as the steepness of this curve changes, then what's happening to n changes. So for example, if n is required to always point away from the surface, here would be a picture showing n. At that point, gravity is pointing straight down. I know that the force in the direction of motion is given by this piece of gravity that points in the direction of motion. In other words, mg points a little bit along this direction, and mg points a little bit like so. This part of mg right here counteracts the normal force. But this part of mg is the acceleration in the direction of motion. Whereas over here, the normal force is starting to point more vertically up. mg still points down. And there's not very much acceleration in the direction of motion. mg is mostly counteracting the normal force. And this part is the only thing that's pushing the object forward. So actually the acceleration in the direction of motion is less here than it was back here. And since the acceleration in the direction of motion is related to the net force in the direction of motion, and this vector has gotten small, then the acceleration has gotten small as well.